It begins without a sound. No explosión, no storm, no warning from satellites. Across the planet, billions of tons of salt simply vanish. First, no one notices. Waves continue rolling toward shore. The tides rise and fall as they always have. Cargo ships cross the Pacific. Fishing boats leave harbor before sunrise. Seagulls circle above familiar coastlines. The ocean looks the same, vast, blue, endless. But beneath the surface, everything has changed. Within hours, marine biologists begin receiving strange readings. Salinity sensors placed across the Atlantic, Pacific, Indian, Arctic, and Southern Oceans start reporting impossible numbers. Not lower than usual. 0. At first, technicians assume equipment failure, a global glitch, software corruption. But as backup systems activate and independent laboratories confirm the data, a realization spreads through scientific networks like a shockwave. The oceans are now freshwater. Not diluted, not partially desalinated. Freshwater. Ships at sea are the first to confirm it physically. Crew members lower buckets, taste cautiously, and stare at one another in disbelief. The water no longer burns slightly on the tongue. Tastes like a lake. Within 12 hours, emergency meetings are called in capitals around the world. Oceanographers try to calculate what should be impossible. Salt doesn't simply disappear. It is the result of millions of years of geological processes. Rivers carrying minerals, underwater volcanic vents releasing dissolved compounds, tectonic shifts shaping chemistry itself. And yet, it is gone. The first consequences begin quietly. Marine life reacts immediately. Most ocean species are not built for freshwater. Fish regulate salt through delicate biological systems evolved over hundreds of millions of years. Cells depend on balance. Osmotic pressure defines survival. Now that balance collapses. Coral reefs begin to bleach within hours. Microscopic plankton, the foundation of the marine food chain, start dying in massive quantities. Invisible to the human eye, entire ecosystems begin unraveling before anyone on land feels a thing. Fishing vessels report something stranger still. Fish are rising toward the surface in erratic patterns. Some move sluggishly, others convulse. By the second day, floating patches of lifeless marine life begin appearing in coastal regions. Governments release cautious statements. We are monitoring the situation. There is no immediate threat to the public. Global cooperation is underway, but the threat is already moving. Salt does more than make oceans salty. It makes them heavy. Salt water is denser than freshwater, and when density changes, physics responds. Ocean currents, the vast, invisible conveyor belts that regulate Earth's climate, depend on differences in temperature and salinity. The Atlantic Meridional Overturning Circulation, the system that carries warm water toward Europe and cold water toward the equator, is driven partly by sinking dense, salty water in the North Atlantic. Now that density difference is gone. Within days, current speeds begin slowing. Satellites detect subtle but measurable changes. Climate scientists realize they are witnessing the early stages of atmospheric destabilization. Weather patterns that have existed for centuries rely on ocean heat distribution. Without it, the balance begins to tilt. Meanwhile, something else happens. Sea ice forms more easily. Freshwater freezes at a higher temperature than saltwater. Polar regions, already cold, begin forming ice faster than usual. Arctic sea ice expands at a rate never recorded in human history. Shipping lanes near the poles close unexpectedly. Insurance companies freeze maritime policies. Stock markets begin reacting. But perhaps the most immediate and visible effect appears along coastlines. The Great Barrier Reef, one of the most complex ecosystems on Earth, begins collapsing almost instantly. Diverse report entire coral structures turning pale and brittle. Tropical fish vanish. Predators lose prey. Within a week, what was once a vibrant underwater city becomes a graveyard. And it is not alone. From the Caribbean to the South China Sea, reef systems fail. Tourism industries begin to panic. Fishing economies tremble. But the largest impact remains hidden in plain sight. Phytoplankton, microscopic organisms drifting near the ocean surface, produce over half of the world's oxygen. They rely on stable salinity to survive. As freshwater overwhelms them, their populations crash. Atmospheric scientists begin monitoring oxygen fluctuations, unsure how quickly effects might surface. Oxygen levels do not drop overnight, but the foundation of global air production has been damaged. And then comes the rain. Without normal ocean evaporation patterns, moisture cycles shift. Storm systems behave unpredictably. Some regions experience intense rainfall beyond seasonal norms. Others fall into sudden drought. Monsoons weaken in parts of Asia. Hurricanes lose some intensity due to temperature shifts, but become erratic, changing direction unexpectedly. Farmers, already confused by global headlines, now face unstable seasons. But there is one consequence that terrifies economists more than dying reefs or altered storms. Salt is not only in the ocean, it is a global industry. Desalination plants, built at enormous cost across arid regions, suddenly become obsolete. Countries that depended on expensive ocean desalination find themselves sitting beside unlimited freshwater. At first, this seems like a miracle. Water scarcity vanishes overnight. Coastal nations begin pumping ocean water inland for agriculture.
Reservoirs fill.
Politicians call it the greatest resource shift in human history. But inland ecosystems are not built for ocean water, even if it is fresh. The ocean contains minerals beyond salt, trace elements that influence soil chemistry. Massive redirection projects begin altering groundwater composition unpredictably. Environmental engineers warn, scale matters. You cannot simply move oceans without consequence. And then the tides begin behaving strangely. Salinity affects buoyancy, which affects tidal friction. As freshwater changes ocean mass distribution and density layering, subtle differences appear in how tides move along continental shelves. Ports report unusual docking conditions. Some ships sit lower in the water than expected. Others struggle with propulsion efficiency because engine calibration assumed saltwater density. Small differences compound, global shipping slows, and in the background, marine extinction accelerates. Whales begin beaching themselves in record numbers, not out of confusion, but because prey species have vanished. Entire migratory patterns collapse within weeks. Coastal communities that once relied on generational fishing traditions find their nets empty. A silence spreads beneath the waves, but perhaps the most unexpected consequence begins in the atmosphere. With salinity gone, the ocean's ability to absorb carbon dioxide shifts. Chemical reactions that once locked carbon in seawater behave differently in freshwater. Scientists race to understand whether oceans will absorb less carbon or more. Climate models fail.
Predictions vary wildly.
Some simulations suggest accelerated warming. Others predict regional cooling severe enough to trigger mini ice ages in certain hemispheres. The uncertainty itself becomes destabilizing. Financial markets dislike unpredictability more than disaster. Commodity prices fluctuate hourly. Water futures collapse. Agricultural futures spike. Energy companies watch polar ice growth with concern, knowing that altered currents may shift drilling access or freeze routes entirely. And ordinary people begin asking a simple question: if the oceans can change overnight, what else can? Religious leaders interpret the event as prophecy. Conspiracy theories spread faster than verified data. Scientists, usually confident in natural laws, now face the unexplainable. Because salt does not disappear without cause. And if something powerful enough to rewrite ocean chemistry exists, it has not revealed itself. By the end of the first month, humanity understands one thing clearly: the oceans were never just water. They were the engine of the planet, and that engine has been fundamentally altered. Coastlines still look familiar, waves still crash against sand, but beneath the surface, the world's largest ecosystem is collapsing in slow motion. And the climate system, the invisible machine that stabilizes life, is beginning to slip out of balance. At first, the change seemed like a gift. Unlimited freshwater, new opportunities, a miracle. But as currents stall, species vanish, and weather patterns shift unpredictably, a deeper realization settles in. The oceans were not broken before. They were finely tuned. And by losing their salt, Earth may have lost one of the most important stabilizers of life ever evolved. Humanity stands on the shore, looking at the same horizon it has always known, unaware that the calm surface now hides the beginning of the greatest environmental transformation in history. Months pass, and the world no longer argues about whether the oceans changed. It argues about what kind of planet remains. The first mass extinction in modern human history is no longer theoretical. It is documented in data centers, satellite feeds, and empty fishing ports. Entire marine food chains have collapsed. Species that survived ice ages and asteroid impacts disappear within a single season. But extinction is only the beginning. The slowdown of major ocean currents becomes measurable to the naked eye. Northern Europe experiences an unusually cold winter, harsher, longer, darker. Energy consumption surges. Power grids strain under demand. At the same time, parts of the southern hemisphere grow unexpectedly warmer. Seasonal expectations fracture. Farmers plant crops at the wrong time. Harvest cycles drift into unpredictability. The planet's thermostat is malfunctioning. Without dense, salty water sinking in polar regions, the great global conveyor belt weakens dramatically. Heat no longer redistributes efficiently. Instead of flowing smoothly across hemispheres, it lingers in some regions and abandons others. Weather becomes extreme not because it intensifies uniformly, but because it destabilizes. Drought grips areas once fed by steady rainfall. Meanwhile, other regions experience relentless flooding as atmospheric rivers shift course unpredictably. Cities designed around historical climate data find themselves unprepared for new patterns. Insurance industries collapse in multiple countries within a year. Coastal economies that once depended on fisheries are now dependent on emergency subsidies. Millions of workers retrain or attempt to. Some migrate inland. Others leave entire nations behind. But the most dramatic transformation is invisible. The ocean floor, once a dynamic ecosystem teeming with life, becomes eerily still. Without marine organisms recycling nutrients, dead zones expand rapidly. Microbial systems attempt to adapt, but the chemical composition of freshwater oceans differs fundamentally from what evolution prepared them for. Some freshwater species attempt colonization. Rivers pour into oceans without resistance. Fish that once remained inland now explore vast, newly habitable territories. In certain areas, freshwater ecosystems begin spreading outward like biological invasions. Lakes and rivers connect seamlessly with oceans. For the first time in geological history, the boundaries between freshwater and marine worlds dissolve. Yet this does not restore balance. It creates a new one, unstable and experimental. Humanity responds with technology. Massive artificial salinity restoration projects begin. Governments consider dissolving industrial salt reserves back into the oceans. Mining companies pivot from extraction to reintegration. Ships designed to distribute concentrated brine deploy across strategic zones. But the scale defeats ambition. The oceans contain approximately 1.3 billion cubic kilometers of water. Resalinating even a fraction would require quantities of salt beyond current global reserves. The cost is astronomical, the logistics impossible within decades. So attention shifts. If the ocean cannot return to its previous state, perhaps civilization must adapt instead. Floating agricultural platforms multiply, with unlimited freshwater stretching beyond the horizon. Desalination is no longer necessary. Coastal megafarms begin pumping water directly from the sea to irrigate genetically engineered crops. First, yields increase, but nutrient imbalances emerge. Ocean water, though fresh, lacks certain soil-supporting minerals in proper ratios. Artificial supplementation becomes mandatory. Farming turns into chemistry. Meanwhile, oxygen production from phytoplankton remains dangerously low. Atmospheric measurements reveal a slow but measurable decline in oxygen concentration. Not catastrophic, not yet, but trending downward. Scientists calculate timelines. If phytoplankton populations do not recover in modified forms, breathable air composition may shift over generations. Biotech companies accelerate research. Engineered plankton strains are released experimentally into contained ocean regions. Some survive. Others mutate unpredictably. Ecological engineering becomes humanity's most urgent project. And while science fights to stabilize the planet, geopolitics transforms. Arctic ice expands significantly due to altered freezing thresholds. New land bridges form seasonally. Nations compete for access to exposed seabeds rich in minerals once unreachable beneath deep saltwater. The balance of global power shifts northward. Countries with cold climates, once disadvantaged by harsh winters, now hold strategic leverage. Energy demands reshape alliances. Migration patterns accelerate toward regions with moderate, stable weather, now rare. The disappearance of salt has rewritten geography without moving continents. Even the sound of the ocean changes. Salt influences acoustic properties of water. Naval systems calibrated for saltwater detection lose precision.
Submarine navigation struggles.
Marine communication technologies malfunction. For a time, the oceans become quieter in more ways than one. But not permanently. Within a decade, evolution begins experimenting. New hybrid ecosystems emerge along continental shelves. Freshwater algae adapt to brackish remnants near coastal estuaries. Certain crustaceans mutate tolerance ranges. Life does not surrender easily. Humanity watches evolution unfold in real time. Children born after the event grow up knowing oceans as freshwater by default. Textbooks describe the saline era as ancient history. Photographs of coral reefs appear alien, vibrant, crowded, colorful in ways their world has never seen. Culturally, the ocean loses part of its identity. No longer symbolic of mystery and depth alone, it becomes a resource, accessible, drinkable, manageable. Coastal cities build direct freshwater extraction systems for urban supply. Water scarcity fades from political debate in many regions. But abundance brings new problems. With unlimited freshwater access, consumption skyrockets. Agricultural expansion accelerates deforestation inland. Ecosystems once protected by aridity become vulnerable to overuse. The planet shifts from scarcity-based tension to abundance-driven imbalance. And still, climate instability persists. Decades after the transformation, the global average temperature oscillates unpredictably. Some scientists believe Earth is slowly stabilizing into a new equilibrium. Others warn that tipping points have merely been delayed, because the ocean's chemistry once buffered change. Salt influenced not only density but also chemical absorption, nutrient cycling, and heat retention. Without it, Earth responds to atmospheric shifts more sharply. Human civilization becomes hyper-adaptive. Cities redesign infrastructure to withstand unpredictable weather extremes. Floating urban districts expand. Autonomous climate monitoring satellites track atmospheric variables hourly. For the first time, humanity actively manages planetary systems not as observers, but as participants. And then comes the final realization. The oceans were never just about water, salt, or fish. They were memory. Layered within salinity gradients and deep currents were records of Earth's climate history stretching back millions of years. That chemical archive has been erased. Future scientists cannot read the planet's past from ocean cores as previous generations did. A geological record spanning epochs is lost in a single transformation. Humanity altered not only the present, but access to its own history. Yet life continues. Freshwater leviathans, enormous evolved descendants of river species, begin dominating coastal ecosystems. Artificial reefs built by humans host entirely new biological communities. Energy grids stabilize around diversified, renewable systems designed for volatile climates. The world does not end, transforms. And slowly, a new balance emerges, not identical to the old one, but functional. The skies remain breathable. The land remains fertile. The oceans remain vast. But something fundamental has shifted in humanity's understanding. For centuries, the sea represented permanence, a constant backdrop to civilizations' rise and fall. Empires collapsed, borders shifted, technologies advanced. Yet the oceans remained saline and eternal. Now that illusion is gone. If something as ancient as saltwater can vanish overnight, stability itself becomes questionable. The freshwater oceans shimmer under the sun, calm and deceptively peaceful. Children swim in them without tasting salt. Ships cross them without corrosion. Farmers irrigate from them without desalination. And beneath the surface, entirely new ecosystems pulse quietly into existence. Earth survives, but it is no longer the Earth humanity once knew. It is an experimental world, one reshaped by an impossible event, forced into reinvention, balanced between fragility and resilience. And as generations pass, one question lingers in scientific circles and philosophical debates alike. Was the loss of salt a catastrophe, or the beginning of a different kind of evolution?